All right, good morning, everybody. So, Stats Unit 5 practice test. Number 1, a statistics professor wants to see if more than 80% of her students enjoyed taking her class. At the end of the term, she asks a random sample of students from her large class and asks in an anonymous survey if the students enjoyed taking her class. So which set of hypotheses should she test? So if we go down the list, okay, what we're mainly looking for here is an equal sign for our null hypothesis. You notice A does not have an equal sign, so we crossed it off. A is bad. B looks good. C is bad. D is bad. Okay, and E looks good for the null hypothesis. So we notice it says more than 80%. So we're going to test an alternative hypothesis that is more than 80%. So between B and E, B it says P is greater than, E it says P is less than, therefore it's going to be B. Okay, A, C, and D do not have an equal sign in the null hypothesis where B and E do. And we know it's going to be B because B has the greater than symbol for the alternative. And if this makes sense for this problem, then it's P is greater than 0.80 versus E, which is less than. Okay. So look for a similar question on your test. You're looking for the null hypothesis to have an equal sign, and you're looking for the less than or greater than symbol to match up with the question. Okay, question 2 says, not wanting to risk poor sales for a new soda flavor, a company decides to run one more taste test on potential customers, this time requiring a higher approval rating than they had for earlier tests. So basically their alpha is going to go lower, okay, a higher approval rating. So that means you're going to increase one type of error while you decrease another type of error, and then it may or may, it will affect the power. The power will either go up or go down. So when you lower the alpha, you risk more of a type 1 error, and while risking a type 1 error, you also increase the power. Okay, so it's kind of weird. You can increase the power that way of your test. However, you increase the risk of your type 1 error. So the best way, remember, the best way to increase power to reduce both types of errors is to just simply get a bigger sample size. So reducing a type 1 error actually increases your power, but you run the risk of a it will increase the type 1 error chance of so by decreasing the type 2 error, you increase your power. Okay, so the answer will be 1 and 3. So look for a similar question. It's pretty much going to be the same thing. So just look for an increase of type 1 error and look for an increase in power. Okay, that's pretty much the only question for this whole test that's got anything but the power. Okay, give me one moment, guys. As far as variations on that question, don't really expect any variations on that question. Just giving you a heads up. This is also, I love this question. It's a good question. It's the best way I can describe power. I know it looks like I'm not, but I feel like it's one of those things that demonstrates power. By changing your alpha. If you lower your alpha, you increase your type 1 error chance. For time, I'm just going to move on. Okay, so once again, this is something that you're going to see on your test. Question 3. Dolphin births. Okay, a state has 2 aquariums that have dolphins with more births recorded at the larger aquarium than at the smaller one. Records indicate that in general, babies are equally likely to be male or female, but the gender ratio varies from season to season. So you got 2 aquariums. Okay, you have a larger aquarium, smaller aquarium. The one in the larger one has more dolphins, they have more births. The smaller one has less dolphins, they have less births. Okay, and it says in general they're equally likely to be male or female. Okay, so there's no oh, dolphins tend to have more male babies than female babies or whatever. They say it's equally likely chance, okay? But the gender ratio obviously varies from season to season. Sometimes more boys, sometimes more girls. There's no rhyme or reason. It's just overall, on average, it equals out to be about 50-50. Which aquarium is more likely to report a season when over 2/3 of the dolphins were born males? So this number doesn't really matter. It's more or less just it's not equal, okay? That you have a sort of far from 50-50 chance. It says in one season it was over 2/3 males. So when you have variance like this, that's if you have two groups and you want to talk about variance, whichever is the smaller group, you would expect more variance. Okay, one more time. If you have a smaller group, you should expect more of a variety, right? More variance. If you have a larger group, that larger group should tend to go towards the average. So if you have a smaller aquarium, let's say that aquarium only has like 4 dolphins. Okay, so it's, let's say 2 boys, 2 girls, and let's say that they have babies every now and again. It's more likely that it's going to be maybe like 3 boys and 1 girl, or 5 boys and 2 girls, or I don't know how dolphins have their babies and stuff. Okay, but it should be about 50-50. And so the more amount you have, the larger quantity, the more likely it might equal out to 50-50. The smaller group you have, probably smaller births or fewer births. Therefore, in 1 year, 1 season, it might be further from 50-50. Okay. One more time. A smaller group, more variance. Larger group, less variance. So a smaller aquarium, because smaller sample sizes are more likely to have greater variance. Okay. You have a large group, you got a small group, male, female is about 50%. Okay, 50-50, but this is greater than 2/3. That's more likely to happen at these smaller aquarium. Questions on that? All right, so let's go through questions 4, 5, 6, and 7. I'm going to go ahead and do them on a separate sheet or on here. That way we can work through them together. Okay. All right. So question 4 is going to say, a can of pumpkin pie mix contains a mean of 30 ounces. Okay, 30 ounces. And a standard deviation of 2 ounces. The contents of the cans are normally distributed. What is the probability that 4 randomly selected cans of pumpkin pie mix contain a total of more than 126 ounces? So we know that in general, the pumpkin pie mix has a mean of 30 ounces. And there is a standard deviation of 2 ounces. So it's like a 30 plus or minus 2. And it says something. There are 4 randomly selected cans. So you go to the store and just pick 4 random cans. So our size, or sample size, is going to be 4. Using that information, we can find our standard deviation of 4 cans. So remember, we don't just have 1 can, we've got 4 cans. Okay, 1 can has a standard deviation of 2, but the standard deviation of the group is going to be different. Okay, the standard deviation of the group is the standard deviation of each individual one divided by the square root of your sample size. So one more time, the standard deviation of the group is going to be the standard deviation of the individual one divided by the square root of the sample size. Okay. Now, if you have 4 cans, okay, if you have 4 cans, we're going to multiply that by each one, which should be 30, which gives us 120 ounces. So we would expect 4 cans to have 120 ounces of pumpkin pie mix because there's 4 cans that are 30 ounces. But we know there's a little bit of variance for each can, but over the larger group, it should be a smaller variance, right? So given all that information, we're going to go ahead and say we're going to find our z-score, which is going to be what it says here at 126 pounds. So what we actually observed was 126. So we're going to say our x minus our x mean divided by the standard deviation. So we're going to say 126 take away 120 divided by the standard deviation that we found here of 1 gives us 6 over 1, which is just 6. So we've got a z-score of 6. I guess I'm circling like a lot of stuff here. So a z-score of 6. What's probability of getting a z-score that's not just 6, but total more than 6? So first, I guess there's no testing we have to do. It's just straight P. Probability of getting a z-score greater than 6 is super tiny. Okay, usually a z-score of 6 is not even on the z-table. Okay, remember, once you get a z-score, you should go to your z-table. So going to a z-table, you usually can't find 6. Usually it'll max at like 3.5 or 3.9 or something like that. And so anywho, to have a z-score greater than 6, it should be a tiny, tiny, tiny amount. It's basically close to 0. We're just going to say less than 0.001. That's usually a standard answer for a tiny number. Okay. Anything greater than like 3 or 3.5, right? Usually you're going to see numbers less than 0.001. Ugh. Okay, depression. A recent psychiatric study from the University of Southampton observed a higher incidence of depression among women whose birth weight was less than 6.6 pounds than in women whose birth weight was over 6.6 pounds, based on a p-value of 0.0248. The researchers concluded there was evidence that low birth weights may be a risk factor for susceptibility to depression. Explain in context what the reported p-value means. There's a lot of ways to look at this and do stuff, but we're assuming, right, that there's no difference whether you weigh less than 6.6 pounds or greater than 6.6 pounds. There should be no difference in reported depression rates. It should be about the same when you find the difference, right? So the null hypothesis would be that you subtract them at 0. If you subtract them, maybe it's different, so it's not equal to 0. You do all this stuff, and what you find is a p-value of 0.0248. Okay, so if there was no difference, okay, if there was no difference, then you would get a study. You would get results, okay, with that probability, like only that many times out of like 100, right? Got 2 or 3 out of 100 chance of getting that result. Okay, more likely, yeah. If it were the same, then it should be closer to 50, you know, a p-value of like 50 or you know, whatever. Somewhere higher than 2%, right? So explain in context what the reported p-value means. So a p-value of 0.0248 means that if the birth weights of women was not an indicator of depression in women, so if it was not an indicator of depression, okay, meaning that there's a difference, okay? If there was no difference, this p-value means that, okay, it would only occur about this many times. So if if you did a study and you got results like this, and you did everything right to collect your information, right? It's really rare that the numbers you'd got for this study, that you got those results, right? Not saying it shouldn't happen, but it's a really low chance of actually happening if this was a study that you did. Okay, you'd be like, wow, these are pretty rare results. So this looks like there's actually a difference between people and their birth weights. You're more likely for this to happen over that or whatever. Okay, so all it is, this is just Mad Libs, right? A p-value of blank means that if a description of this, okay, then the study's results would occur at about, change it to a % of the time. All it is, Mad Libs. Okay, give me a small number that's less than 1 but greater than 0. Give me a decimal between there. Okay, that's your Mad Lib number. Change it to a percentage. Okay, that's the last number. And then give me a situation that compares things. I don't know. It's all just Mad Libs. Okay, just fill in the blank. A p-value of blank means that if blank, then the study's results would occur at about blank % of the time. And those numbers match up. Okay. All right. Questions, comments, concerns, anything big you want to talk about right now? Or let's go on to question number 6. Okay. All right. Question 6 is a fun question. Let's get our calculators out. Let's do some calculator work. Question 6. All right. So question 6 goes into truckers. Okay. On many highways, state police officers conduct inspections of driving logbooks from large trucks to see if the trucker has driven too many hours in a day. At one truck inspection station, they issued citations to 49 out of 348 truckers that they reviewed. Based on the results of this inspection station, construct and interpret a 95% confidence interval for the proportion of truck drivers that have driven too many hours in a day. So let's take a look here. This says there was 49 out of 348. So our observed amount is 49 divided by 348. So that means, what did we observe for the other people would be 348 minus 49, which is 299. Divide that also by the sample size of 348. And what you get are two proportions, right? This is like the success proportion, failure proportion. 49 divided by 348 is 0.14, round that up to 1. And that means I could even do this. It should be, that should be that. Let's double check. Yep, perfect. All right. So we have those proportions. We have a total sample of 348. And our Z star, because we're doing 95% confidence interval, is going to be 1.96. Okay. Let's start by looking at our confidence interval. Our confidence interval is made by taking our average plus or minus our margin of error, and the margin of error is that Z star times our standard deviation. Standard deviation we have not calculated yet, so I'll just write that out as P times Q divided by N, but you square root the entire thing. So our margin of error is going to be equal to our Z star 1.96 times, okay, the square root of this times this divided by that. So 0.141 times 0.859 divided by 348. And the whole thing is square rooted. So 0.141 times 0.859, divide that by 348, square root that whole last answer, multiply that by 1.96, and that is my margin of error. So 0.0366. So someone's going crazy here. Let's just cut it off right there. We can call it 0.36 or 0.37. I'm just going to go ahead and call it, keep it consistent with my last step, 0.036. I think if we were rounded, I probably would have rounded to that. So I've got all this information. Now I can build my confidence intervals. One more time, my observed value, 49 out of 348. The other value would then be this minus this, 29 out of 348. So those, that's my success and failure. Sample size of 348. My Z star will use 1.96. Okay, because of 95%. If this was different, that would be different, but we're not going to do different right now. Confidence interval we're going to build is going to be this plus or minus that. So this number plus or minus the number we're going to find using this formula. Z star times the standard deviation, which is P times Q divided by N. So root that, and that's what I get. All right. Confidence interval, 95% confidence interval. P hat, so 0.141 plus minus this number we found for the margin of error, 0.036. So I'm going to go ahead and start by subtracting to get my lower number, okay, the minus number first. So 0.141, take away 0.036. Okay, so this minus that to get my left number, which is 0.105, which is about 2.5%. And then the same thing, but N gives me the right number for my interval. Same numbers. Adding, I get about 0.177, which is 17.7%. So that's my interval, low number, high number, right? Oops. And what I'm left with, right, is this interval. So that means that they did a little survey, right? This is what, just in one day. And one day, out of 348 trucks that had stopped by, or truckers, I guess, that drove their trucks into the station, 49 out of 348, so about 14% in one day. Yes, so they're doing their samples from one day. So then we would kind of expect, yeah, 14% might not be the actual number every day. So overall, what's the general percentage of all truck drivers? Based on that one day, we expect it to be maybe not always 14%, but between 10.5% and 17%. So a little bit lower, a little bit higher, but somewhere in between that range there. So we would say something like, to give some sort of interpretation, right? We constructed it, now we got to interpret it. Oops. All right, so when we say 95% confident, that just kind of means that, missed the end. I am 95% confident that the percentage of truck drivers driving too many hours is between this number and that number, okay? So by 95% confident, that means that if we did this, right, like 100 times, that 95% of these would capture the real numbers, and it would be between this number and that number, okay? Right, that there's a small itty bitty chance the real one's not captured within there, but we're pretty sure the actual number's between those two numbers there, okay? All right, almost done. This last one is super awesome. This last one, the main reason why I'm redoing this whole thing, so I made a small mistake in my last class doing this, because usually we use a calculator to calculate this stuff. So I might just cancel this one, but I like it a lot. It's great. It's tough. It's fun. Okay, so this is kind of going to the last thing that we did, last chapter with comparing two sets of data. Each year, people who have income file income tax reports with the government. In some instances, people seek advice from accountants and financial advisors regarding their income tax situations. This advice is meant to lower the percentage of taxes paid to the government each year. A random sample of people who filed tax reports resulted in the data in the table below. So here's the percent that paid lower taxes. So they paid a lower percent of taxes. Yes or no? They had tax advice. Yes or no? So for example, if you did not have tax advice, but you found out later that you paid lower taxes than if you did, okay, maybe they would have changed some situations. Okay, they would pay lower taxes, yes. Didn't pay lower taxes, no. They missed some items, okay, to deduct whatever. Percent paid lower taxes. So let's just say, yes, they had advice. This looks like a majority of them actually paid a lower percent of taxes, okay? So let's take a look at how we set this up. There's a lot to unpack here. So let's start by looking at a few things. I like to kind of put these margins in and say 48 plus 19. Well, that equals 67. 24 and 86. You add those together, add this 110. Let's add these down and get 48 and 24 is 72. Add those down, 1986 is 105. If I add those across, add those down, I get 177. Okay, so this is kind of like my n, like my n, my total, all the way across and down. So, since we're trying to compare tax advice, okay, we're going to kind of look at this going down that way. Okay. So, do they pay lower taxes? So our P, what we're trying to observe here is lower taxes, right? Did they pay a lower amount of taxes? And for no, okay, we'll call this PN, PY, okay? Yes, they had advice. No, they did not have advice. So for those that did have, all right, this will make my P and my Q. So if they had advice, it would be 24 out of 72. My P of N would be 24 out of 72, which would give me about, right, 33%. My P for yes had advice would be the 86 out of 105. Okay. And 86 divided by 105 is going to be 0.819. So if we want to find our Q value, our Q would be 1 minus that number, which is 0.667. And my Q of this would be 1 minus this number, which is 0.18.1%, 0.181. Okay. All right. So I'm assuming that there should be my null hypothesis here, right? My null hypothesis is that if I were to subtract these, that my yes minus the no should be 0. The alternative is what? Lower the percentage. So is there a higher percent of people that paid lower taxes? Remember, our P, what we're observing is lower taxes. Did they pay a lower amount of taxes? The yes minus no should result in a greater number. Should. All right. So I'm trying to test this, and before I test this, I have to do my standard deviation of the difference here. And the standard deviation of the difference is going to be P times Q divided by N. Let's do my yes first. Okay, so P times Q, so 0.819 times 0.181 divided by its sample size of 105. Add that to P times Q divided by N of my no. Okay, so P times Q is 0.333 times 0.667 divided by its group of 72. And what I get when I do that, let's see. Square root, parentheses, parentheses, the left side, 0.819 times 0.181 divided by 105. Add off. Add that to close that off. Did I do that correctly? And I did. All right, so I get 0.067. Let's just use that. Actually, let's do one more. We'll run that up. Okay, P of Y minus P of N, standard deviation of that. So remember oh yeah, I have not found my mean yet. Remember my mu? My mu is simply Py minus Pn. So mu would be 0.819, take away 0.333. So as I say, my average is going to be 0.486. Whew. Let's find our z-score. The z-score, which will help me with my p-value. My z-score is going to be what I found for my average with mu minus my Null hypothesis, this whole difference here where it should be, which is always going to be 0, and divide that by your standard deviation difference. So I get 0.486, take away 0, divided by 0.0671. So I get a value. Take away 0. Okay, divide that by 0.067. And I get 7.2, let's call that 7.24. Okay. So what is the probability, the p-value here is the probability of getting a z-score that is greater than, hold on. Yeah, I'm going to put greater than 7.24. So once again, go into our z table. The z table here doesn't even go to 7.2. So similar to the last one, it's going to be less than 0.001. It's going to be a small, tiny, itty bitty number. Okay. If we go to a z table, where's my stats book? Oh my. I'm being silly and I can't find my stats book offhand right now. It's because it's behind my computer. So just to show you guys once again, these z-scores, these z-tables that come from your book, come from wherever, okay? A z-score, this here only goes to 3.89, which is 0.9999999. And remember, this is just the left side shaded, so right side shaded would be even smaller. So it's a tiny number. In fact, you can even add an extra 0 there if you want to be more specific, but it is a tiny, tiny, tiny number. Okay, so because you have a tiny p-value, you should reject the null hypothesis. That is evident. There's so much evidence here, right? 81% versus 33%. It's a huge gap there. Okay, so we are going to essentially reject the null hypothesis and accept that the evidence strongly suggests that getting tax advice will lower how much you pay, okay, because of that p-value. All right, so this has been recorded. I will post this shortly. It's almost the end of class here, so for the sake of time, I won't really be able to answer any questions right now. I apologize, but Thursday morning we will have a chance to review this, all these items. Okay, we can go back over this again on Thursday before you take your actual test. Okay, so I'm not even going to release the test till Thursday to give you guys time to get caught up and to review this practice test. All of that for 0.001, exactly, Javen. Like, it's obvious right here that it's 81% versus 33%. That's cool. That's great. That's awesome. However, by finding that z-score and finding that p-value, that's just the final steps to confirm, like the nail in the coffin, that there's a huge, well, according to these numbers, there's a huge difference getting tax advice versus just doing it on your own. According to these numbers here, this is just kind of made up numbers or whatever. So, yeah. Anyways, you have any questions, stay back. They got to be kind of short questions. Other than that, have a great, awesome, wonderful day. I'll get this video posted. Okay. All right.